Couple different topics today, the first of which is called impulse. And impulse is essentially a new definition or a new way to say change in momentum. And so instead of just having a delta P for a change in momentum, now we call it impulse. It's the same variable. You solve it the same way, but there's a little bit different equation for it that you can supplement to use the current delta P equation. Okay? So right now we think of the change in momentum as this equation. Delta P equals m delta v, right? But now this is an additional one that you can use to solve for the change in momentum. And so capital F stands for what? A force, right? Some sort of force over a certain amount of time. It tells us the change in momentum, okay? So change in momentum can either be equal to force times delta t, right? Force times time, or mass times the change in velocity. Okay, we don't really need to look at these two. Okay, I just want you to have that equation. So this equation should probably go on your equation sheet. I don't need you to have these two. But knowing what we know about the original equation, if both of these are set equal to delta P, what can we do to those two equations? Set them equal to each other. So this is an additional equation that I think might be helpful for you to have down. Okay, it will show you that both of these can be set equal to the change in momentum. So since they both equal delta P, we can just set them equal to each other. So this one could be helpful if you're not given the change in momentum or something like that. Okay. So there's not a whole lot else we need to talk about impulse. We're going to try just a couple here. What force is needed to bring a 75 kilogram object traveling 44 meters per second north to a stop in 2.1 seconds? Okay, so this doesn't even mention the word momentum or mention the word impulse, right? But what it does give you is it gives you a mass, a velocity, and a time. Okay, so if we set up our equation, force times delta t equals m times delta v. Okay, we're solving for a force. Delta t, remember, is always just going to be the time that they gave us, right? We don't have a final time and an initial time. It's just going to be what they gave us right there. So 2.1 equals m times final minus initial velocity. So what's our final velocity here? 0, because it says it comes to a stop. Okay, so final needs to be 0, initial is 44. Okay, that's really important. You don't have your calculator at lunch, go ahead and grab that. Okay, is that about what we had? Multiply these two on the right, divide by 2.1. What does this negative tell us in terms of our force? What's the negative tell us?
That is stopping.
Yeah, that's right, it's going against it. So since our original velocity was north, that means that this is south. So you could also give your final answer at 1571.4, 4 newtons south, right? If we're going north and we want to come to a stop, the force has to oppose that. So it could be friction, it could be an applied force of some kind. It doesn't really matter to us what type of a force it is, but something is opposing that velocity to slow it down and bring it to a stop. So we have to include the negative there or the south, okay? One or the other, but not both. Okay. What's the change in momentum that's acted on by a 64 Newton force for 3 seconds? Okay, so it might ask you for the impulse or it might ask you for the change in momentum. Those two mean the same thing, right? Change in momentum is delta p, right, which also means impulse. Okay, and we have two equations that we can use to solve for that. However, in this problem, they give us a force and they give us a time. Okay, so it's literally as easy as it seems. Okay, here they didn't give us a cardinal direction, right? But since our initial force was positive, we need to leave our units aren't newtons. Sorry. For momentum, they're either newtons times seconds or kilogram times meters per second. Either one is fine. Okay. The reason it would be newtons seconds is because we're taking force times time. Okay, those two mean the same thing. Okay. But since our original force is positive, that means our momentum has to be in that positive direction as well.
So technically that way was like 3 minutes.
That's right. Any other questions? Okay. All right, let's try this one. A 4.3 kilogram object is dropped from a height of 8.4. What's the momentum of the object after it has fallen 3 meters? Okay, so we have to use our kinematics here like we did on our homework, okay, to find our velocity before we can do anything else. Okay, so there's a couple different ways that we can look at this problem. So here's where my object starts at a height of 8.4 meters. But does it drop all 8.4 meters? No, it only drops a total of 3 meters. Okay, so if we're looking at using our kinematics to solve for our velocities, we can just really use our 3, right? We're going to know that it ends up 3 meters below where it started. You can do it a couple different ways, right? You could say your initial displacement is 8.4, your final displacement is 5.4, right? Or you could say your initial displacement is 0 and your final displacement is -3. Does that make sense? You need to set kind of your origin one place or the other. I always like to put my origin here, which means when I'm looking at my kinematics, I would say my distance initial is 0, and my distance final is -3, right? That's how I would set that problem up, because I'm going to always want my initial displacement to be 0. My final displacement ends up 3 meters below where it started. Okay, does that part make sense? If you wanted to do 8.4 and 5.4, it would work out mathematically exactly the same. Okay? All right. What's our initial velocity of a dropped object? 0, right? Since we say it's dropped, our initial velocity is 0. Our final velocity is what we're solving for, right? We want to know what's our speed after that 3 meters. What do we know about the acceleration of a vertical object? Gravity, right, good. -9.8. Okay, so if we think back to our kinematics, which I know was a long time ago, we need to pick a kinematics equation to help us solve for that. Okay, we don't have time, which eliminates 2 equations for us. Okay, so which one should we probably use? The third. Okay, are we on the same page so far, or am I moving too fast? Okay. So our third equation looks like this. Vf squared equals Vi squared plus 2a df minus di. Okay, V final is what we're solving for. V initial is 0. -9.8 and -3. Okay, because we're ending up 3 meters below where we started. Okay, is that what we had our final velocity at? What do I need to add to that? A negative. Why do I have to add the negative? Because it's going downward. Remember, anytime we square root something, our answer technically comes out plus or minus that number, right? Mathematically, that's how it works. It comes out plus or minus 7.67. So we have to decide, is that final velocity going up or is it going down, right? So since it's going down, we have to leave it negative. So you have to add that, right? Your calculator will not do that for you. Okay? What's the momentum after it's fallen 3 meters? So we need to take our change in momentum here and say mass times final velocity, negative 7.67, minus initial velocity, which is 0. And we get a change in momentum of about negative 33 kilograms times meters per second. Okay, does that make sense? You need to be able to solve those kinematics equations in these chapters. Okay, so I know it's been a while since we've done kinematics, but it's still going to come up. Okay. Force of 25 newtons acts on an object for 0.23 seconds. It accelerates it from rest to 1.29. What's the mass of our object? Okay, go ahead and try this one on your own. Is that about what we had? Okay, from rest, right? This tells us that this is our initial velocity. This is our final velocity. So that's why we did 1.29 minus 0. Okay. Questions here? All right. So we are going to move now into a little bit more intense collisions. We have two different types of collisions that we talked about. What were they? Elastic and inelastic. And what type of the collision is it when the two end up apart? Elastic, right? When they bounce off of each other and they end up as two separate objects, that's an elastic collision. And so we're going to look at both of these collisions now in 2 dimensions, which means they're not just moving east and west, or they're not just moving north and south. They're coming in at angles, they're colliding with each other and doing different things than just being in one line. Okay, so elastic collisions in 2 dimensions. We're going to look at both types today. But this means we're going to have to be really good at vector addition again, right? So breaking our triangles down into x and y components, all that kind of stuff, okay? So I'm going to give you a couple seconds to get this written down or get written down what you need to, and then we're going to walk through what it takes to solve a 2-dimensional collision. Luckily, it's not a new equation of any kind. We just now have to start looking at everything in the x direction and then everything in the y direction. Okay, so go ahead and get written down what you need to here, and then we're going to walk through this together. Okay, so this is my attempt at drawing what's happening here. We have a red one, right? The steel puck that has a mass of 0.5. It's moving east. It collides with one at rest, and then it's going to bump these two things. So rather than this being a perfectly elastic collision and them just exchanging velocities, we see now that they bump each other, right? And they're going to move them in different directions. So after that first one collides, it's going to end up going this direction, right, up into the east. So where could we envision that the green puck is probably going to go? Right, visualize what's happening here. One's moving to the east, and it ends up bumping this direction, right? So where would we think this one that's at rest is going to go?
Can you just go like southeast?
Yeah, it should probably go southeast, right? It's not going to do anything crazy and go through it, right? So realistically, our second puck should end up somewhere in that direction, right? That's what our goal, that's what our thought process might be, okay? Now, lots of things affect that, but the fact that this red puck has a larger mass and a velocity to start with tells us that it's going to bump that green puck to the east somewhere, right? So this is how we start going about this. We're going to use our m times v equation. Look at your equation sheet for elastic collisions. It looks like that. m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. You see what I'm talking about? Right? Those are all of the variables that we're going to use, except we're going to do the equation 2 times. One in the x direction and one in the y direction. Okay? So we have to solve things purely in horizontal and then purely in vertical, and then we'll combine them at the end. Okay? So the first thing what we need to do is break down all of our variables. So m1 is 0.5, right? This is our first object. And then we're going to have basically double the variables because we have v1x and v1y. Okay, so instead of just having an initial velocity, you have an initial velocity in the x direction and an initial velocity in the y direction. It doesn't mean that all of those always have a value, right? They might be 0. Well, in this case, one of them is. But we're also going to have a v1x prime and v1y prime. Right? What's the prime or that apostrophe mean again? What's this prime here mean? After the collision. Good. Okay, so as we start kind of getting all of our variables picked out, now let's start putting numbers with them. Okay, so we can't just have an initial velocity of the first object. Now we have to have it in the x direction and the y direction. So it tells us that our first object was moving 2.4 meters per second east. So is that an x velocity or a y velocity? X. And is it a positive x velocity or a negative x velocity? Positive 2.4. Okay? So is that object moving in the y direction at all before the collision? No. So that means v1y is 0. Okay? Does that make sense? Okay. After the collision now, it tells us it's moving 1.8 meters per second at 30 degrees north of east. So we have to break that down into an x side and a y side. Okay, so I'm going to go redraw that triangle right here. Okay, 1.8 is our hypotenuse. North of east means that it needs to touch the east axis, right? And our 30 degrees goes right here. So if I labeled my sides, this would be v1y prime, right? It's the vertical speed of my first object after the collision. This side would be v1x prime. Okay, are we on the same page with that? So let's go ahead and break down that triangle. Make sure that your calculator's in degrees, not radians. Okay, so to solve for y, I would take 1.8 times sine of 30, and that means my v1y prime is 0.9. Is that what you had for that? Okay, am I going too fast?
No, I'm just...
Okay, to solve for v1x prime, we're going to take the hypotenuse times cosine, because it's the adjacent side to that angle.
Where is like the v1x and v1y? Where's that coming from? Like,
This right here.
yeah.
Okay, so when we start looking at our equation, m1 v1 plus m2 v2, right? That whole equation, we're going to solve it one time in the x direction, and then we're going to solve the same equation in the y direction. Oops. So this will really be x. Right? And then we're going to do the whole same equation again in the y direction. So we have to do it 2 times now. So that's why we're going to have one of each. Okay? So these problems take a lot of space paper-wise. I'll just tell you that. It's a lot of work. Okay? So just be prepared. Okay? What did we get for v1x prime? 1.6? Okay, and are both of those components positive? Yes, because one's going north and one is going east. Okay? So do we have any questions about where any of these numbers came from? The mass of our object does not change, so it's okay, it's staying there. Let's look at the green puck now. So we'll say M2 is equal to 0.3. Okay? And we have V2x. That's before the collision. V2y is before the collision. V2x prime. And V2y prime. Okay. So knowing what we know about it starting at rest, what does that mean both of these variables would have to be? I need more than just one person answering. What would it mean if we're starting at rest? What do these components mean? Have to be. 0. Does everyone understand that? We're starting at rest. So our initial velocity is 0 in both dimensions, both directions. But it's not moving at all. So it doesn't have a horizontal velocity or a vertical velocity. Okay? Then after the collision, we want to know what's the speed and angle of the second puck. So we need to solve for both of those variables. We need to solve for v2x prime, and we need to solve for v2y prime. Okay?
So it's like starting over to here, that's why it's 0.
These zeros right here? Yeah, it's starting out at rest, so it doesn't have any initial velocity at all. Okay, not in the x direction or the y. V2x prime is what we're going to solve for. So we're going to solve for its velocity and its direction after they collide. All right, we want to know what's happening here. Okay, so now let's look at how we solve this problem. We have to do our momentum equation, or our elastic collision equation, 2 times. One in the x direction and one in the y direction. So let's do x first. Okay, so when I go to solve these, I try to stay as organized as possible because I want to make sure that I'm knowing that I'm talking about x. So I usually say p in the x direction, right? That's momentum in the x direction. And then I kind of draw this little box for myself. Okay, that in no way affects the problem. You do not have to do that. But what this is my way to stay organized. So if you see me do that, that's why. It does not affect the math. You do not have to do it. I'm just telling you that's what I do. Okay? So right now I'm going to solve the elastic collision equation that looks like this. M1 times V1x plus M2 times V2x. Okay? Equals M1 V1x prime plus M2 times V2x prime. Right? You don't need to write down this whole new equation. This is our equation for elastic collisions, but it's only in the x direction. Does that make sense? Yes or no? Okay? So I'm going to pick out these variables, right? You don't need to rewrite our equation at all. We're just picking out the x variables. All right, so I take M1, which is 0.5, V1x, which is 2.4, plus M2, which is 0.3. Our initial velocity, V2x, is what? 0. Okay, if it helps you to kind of, cross off the numbers after you put them in, that way you can kind of identify what variables you've used and what ones you haven't, that's fine, you can do that. Okay, M1 doesn't change. V1x prime, right, is right here. So 1.6 plus M2 times V2x prime. And I'm sorry, I know M2. I just forgot to write it in there. So this M2 needs to be 0.3. Okay, so do you see out of all those variables, we only have one that we're missing, right? v2x prime is what we're solving for right now. What's the x velocity of our object after our collision?
What is that EC for?
This is just telling us that this is our elastic collision equation right here.
Extra credit.
Okay? Elastic collision in the x direction. Okay? So algebraically, let's solve here.